If I'm curt with you, it's because time is a factor. I think fast, I talk fast, and I need you guys to act fast if you want to get out of this.
In 2014, Martin Fowler, James Lewis, and others published an article outlining and popularizing the concept of a microservice architecture. This started a trend, for better or worse, of decomposing monolithic applications into microservices applications, which has been taken even farther in recent years with the popularization of serverless architecture encouraging further decomposition of applications into simple functions. Cheeky memes aside, I'm not here to debate the relative advantages or disadvantages of these architectures, but a downstream impact of these trends has been an increased pressure in the Java ecosystem on improving startup performance. Being an open ecosystem, Java developers have a number of options for improving startup performance. At the framework level, there's Quarkus and Micronaut, which heavily advertise their startup performance benefits. And even options at runtime level, like, for example, GraalVM, which can be used to create a native image, as well as others. They also come with trade-offs. Adopting a new framework might mean needing to rewrite an existing application, or at the runtime level, making design choices to fit within technical limitations. There is, however, one option for improving startup, often overlooked, that while perhaps not delivering as much benefit, also doesn't require code changes nor has imposing technical limitations: CDS, which is the subject of this episode of Stackwalker. If you're interested in learning more about CDS, other Java topics, or how to find a local Java user group, and more, be sure to check out dev.java, link in the description. To understand how CDS improves the startup process, we must first understand what the JVM does at startup. For that, it can be demonstrated using the humble Hello World program. You can even follow along by including verbose class and xchar-off in your Java command. But don't worry too much about the xchar-off right now, we'll get back to it eventually. On executing the Java command, you will see the output looks something like this. What is happening here is the JVM is loading and initializing the main class, and is then loading all the classes it needs to run the main class. Looking back at the main class, the first class that needs to be loaded is string. To load an initialized string requires loading and initializing all classes string depends upon. String, like all classes, extends java.lang object. String also implements serializable, comparable, char sequence, constable, and constdesc. If we go back to the output, we see these are the first 7 classes that are being loaded. Of course, these are only the first 7 classes. In total, some 469 classes will be loaded and initialized if you're using JDK 20 like I am. What and how much is being loaded isn't the only important part, but from where also matters, which we can see if we look to the right of source, which is rt:/java.base. jrt:/java.base is referencing the JDK home directory on your system, and moderately confusingly not referring to the java.base in the jmods directory, but instead the modules file under the libs directory. If you're on JDK 8, or I shudder to think earlier, this would be under jre-lib and the rt.jar file. The output when running Hello World would also be somewhat different as well. When the JVM loads classes from the file system, it must go through several steps. If it is loading classes from an archive, as would often be the case, first it must decompress the file, which is based on the zip archive format. The JVM will then verify the class is structured correctly. It must then parse the class. These steps are repeated for the hundreds of classes that are loaded every time the JVM is started. Additionally, for each JVM running, these classes would be loaded separately to memory, leading to duplication of these classes in memory. If there was a way to skip some of these steps, we might see a measurable improvement in startup performance. With CDS turned off, which is handled with the xchar-off VM argument from earlier, Hello World executes in about 1/10 of a second. With CDS on, in this case set to the default mode of auto, which we will cover in more depth later, about 4/100ths of a second is taken off of startup time, or about a 40% reduction. We'll look at this in more depth later as well. And just as a note, all test results are done on my work laptop, which is a 16-inch 2019 MacBook Pro. Specific results will vary based upon your own hardware and of course application being executed. But let's get back to CDS. So that's a brief overview of what the JVM does on initialization and how CDS helps to speed that process. To get the full story of CDS, we need to go back to 2005. It's the end of the Star Wars prequel trilogy and the start of the Nolan Batman trilogy, and JVM engineers are dealing with users impatiently waiting for the applications to start. I guess some things never change. You might have noticed I said 2005, and the astute among you would note that 2005 comes before 2014 and the trend towards microservices and beyond that I covered in the intro. When CDS was originally conceived, the goal wasn't to improve the startup of Java applications running on servers, but to improve the startup and reduce the memory footprint of Java applications, often GUI applications, running on client desktop machines. Because you see, back in 2005, hard drives were still hard drive disks, and 512 megabytes of memory was considered ample. On modern hardware like my laptop, with its solid-state drive and 32 gigabytes of memory, even without using CDS, Hello World executes in about a tenth of a second. And the 15 megabytes of class data that JVM loads at startup represents about 0.05% of system memory. In 2005, file on a hard drive disk was much slower, and 15 megabytes represents about 3% of 512 megabytes, and of course, CPUs were less powerful. Because the startup work we covered in the previous section was essentially repeated every time a JVM was started, it was something of a Sisyphean effort. The JVM pushing the rock of class loading up the hill every time on startup, just to discard it all when the JVM was terminated, only to have to repeat this work again. This was an obvious target for improvement. CDS was added during one of the update releases for JDK 5 in 2005. While all the platforms that JDK ran on had support for CDS, only on Windows would it work out of the box. Windows was targeted as this was the platform most clients using Java were on and also had the most significant performance issues. CDS works by loading class data from an archive at startup. This archive contains the class data the JVM needs that has already been decompressed, verified, and parsed, significantly reducing the work the JVM needs to perform at startup. Only Windows uses by default, as these archives are platform specific and can only be generated by having the JVM perform a training run, which happened during the installation process on Windows machines. Though if you're on JDK 11 or earlier, and not on Windows, you can create a CDS archive of the core JDK classes by simply running java share dump. I'll cover what's happening here in more depth in the next section, as well as why it's only relevant to JDK 11 or earlier. So far I have been referring to CDS as well, just CDS, and you might be wondering why I'm referring to the shared archive as well shared, and how all this reduces the memory footprint of the JVM. So CDS originally stood for class data sharing. When a JVM with CDS enabled loaded the shared archive, it would memory map its location. This way, if multiple JVM instances are running on the same machine, they could use the same archive, reducing the overall memory footprint of the two or more running JVMs. I've avoided covering this as the class data sharing aspect of CDS is no longer actively supported. In the years since the CDS's initial deployment, memory has become much cheaper and more available. And on the server side, Java applications are deployed in tightly fitted containers where they are the sole running process, negating the advantage of shared memory mapping. While the name CDS remains, it no longer stands for class data sharing. While the data sharing aspect of CDS is no longer actively supported, the CDS team has been busy adding new features and capabilities to CDS in recent Java releases. Eagle-eyed Java developers on Linux and Mac platforms who have migrated to JDK 17 might have noticed a small change when running Java version. At the end of the output, sharing is printed. This is a result of JEP 341 introduced in JDK 12 that included a default shared archive, in fact 2 shared archives for all 64-bit JDK platforms. They are located under the lib server folder in the Java install directory. They are classes.jsa and classes no co-ops.jsa, as JVM arguments like use compressed ops can impact the structure of the shared archive. This is why I mentioned earlier that Java shared dump is only necessary on JDK 11 or earlier. On the subject of creating an archive, this has also been expanded. JEP 3.10, introduced in JDK 10, expanded the ability of CDS to also track application classes loaded by the JVM at startup. This is very significant, as while several hundred core JDK classes are loaded on startup, even relatively trivial real-world applications might be loading many hundreds or even thousands of classes on startup through their dependencies. Initially, the only way to create and use an archive with application classes was through a three-step process. The first step would require a training run of the JVM, where the JVM would generate a class list of eligible classes to be archived, which can be done with the dump loaded class list argument, like in this example. Viewing the class list file will show the classes the JVM loaded at startup, as well as an ID indicating the order in which the classes are loaded. The next step would be to use that class list to generate the CDS archive. This is done by setting CDS to dump mode with shared dump, telling it to use the class list file generated in the previous step using shared class list file, and defining the archive file to dump to with the appropriately named shared archive file VM argument. Including the application you'll be using the archive with isn't necessary, as the JVM will only be reading the class list and dumping the generated class data to the archive file. Finally, the last step would be to use the shared archive. Here I am using share on. However, this should only be used in a test scenario. Share on requires the archive file to be present and correct, or otherwise the JVM will fail at startup, which is good for validating a newly created shared archive file is present and structured correctly. The default setting is share auto, which doesn't need to be included in your Java command, and is the only setting you should ever use in production, as the JVM will fall back to loading the classes off the file system if the archive is not present or otherwise not structured correctly. Also, briefly going back to the default archive with shared dump, it's worth noting that this also creates a shared archive the exact same way. And the only magic happening here are default values as substituted for shared class list file and shared archive file. Specifically, the class list provided under the lib folder in your JDK home directory and JDK home lib server classes.jsa respectively. You can even see that if you run this command, that JDK home lib server classes.jsa will be updated on your system. With JEP 3.50, part of JDK 13, a simpler way of creating CDS archives was added, Dynamic CDS Archives. This update allowed a CDS archive to be created in two steps. A training run was still required, during which you will use archive classes and exit, which, as the name suggests, will create a shared archive when the JVM exits. On subsequent runs, you would then reference the generated archive. Finally, in JDK 19, the process of creating and using a shared archive was simplified into a single command with JDK 8261455. This command added the autocreate shared archive JVM argument, which essentially works like an if-else statement. The JVM on startup will check for the archive file defined with shared archive file. If not present, the JVM will then generate an archive at shutdown. If the archive is present, the JVM will load from the archive. Additionally, if the archive is no longer valid, such as if the archive was created with an older JDK version, or a dependent jar has changed, a new archive will be generated. The most significant advantage for this method is that the same Java command can be used for building and using a CDS archive, reducing possible confusion and maintenance work of having two Java commands, one for creating the archive and another for using it. Expanding CDS to cover application classes greatly increases the benefits provided by CDS. To demonstrate, we'll use the Pet Clinic app the Spring engineering team put together, link on the screen and in the description. Starting Pet Clinic with CDS disabled usually takes about 5 seconds before the application is ready. Using just a default archive, these numbers drop to about 4.8 seconds. However, when we create a CDS archive for the Pet Clinic app and use that at startup, startup time drops to 4.1 seconds, providing a roughly 18% reduction in this simple example. So let's drill a bit deeper into what's in the box.
What's in the box?
Archive For this, the CDS team has provided tools for inspecting the contents of an archive. Let's first get an idea what the default archive looks like. For context, I'm using JDK 20 on macOS. As mentioned before, these archives are platform specific, so some of the numbers you see will vary depending upon OS and JDK version. Running the above Java command, which I'm not going to repeat, will output a lot of data to the console. Looking near the end of the output, you will see a table laying out the high-level statistics of the contents of the archive. Like here, showing the total number of classes in the archive is 1470. A bit farther down, a larger table is printed, of which only a small portion is shown here. This segment showing there are a little over 41,000 instances assembled in the archive, taking up 1.6 million bytes. Near the end of the table, the total of all the instances is shown, coming up to about 13 megabytes. Note that the shared archive is less space efficient than the JMod or jar archives it is pulling the class data from. The goal is to improve startup performance, and with storage space also being very cheap, the trade-off of increased storage needs is often a reasonable one to make. Going back to inspect the archive file, this command also creates a file, cds.map, that lays out the memory location of all the archived objects. This file can be searched to review the memory locations of the archived classes, like in this example, looking for the instances of Java Lang object. As we see, CDS improves the startup performance of Java applications. Naturally, many Java developers when hearing this would associate this benefit with the production applications they are supporting. And while CDS will be beneficial there, CDS might provide the greatest benefit when used with shorter running applications, as startup time makes up a larger fraction of total runtime. There are a set of short-lived Java applications often run by Java developers, Java Compile, as well as other processes in their build pipeline like automated test suites, which typically have a runtime of a few seconds to a few minutes. Using CDS here can help reduce build time through reducing the startup time of these applications. Additionally, there have been a number of recent and upcoming changes to Java that make it a more practical choice for short-running utility apps and scripts. You can learn more about that by checking out this episode of the Inside Java newscast. But here again, CDS might be beneficial as these applications also typically run for only a few seconds or minutes. To see an example of this benefit, running Java C on Hello World typically executes in just under a second. When using CDS with Java C on Hello World, execution time is closer to a half a second. It's also possible to include this functionality into build tools like Maven, like here in this example with Maven's compiler plugin. CDS has seen many improvements over the past several years, but there's still more in the future. In the near term, the CDS team is looking at expanding the scope of what can be included in the CDS archive by including array classes in the archive, Lambda forms, or older classes compiled in JDK 5 or earlier. This last example might sound a bit arcane, but some popular Java libraries like ByteBuddy in fact have many such classes compiled to JDK 5 for compatibility reasons. The biggest change in the future for CDS though is that it's a central part of Project Layton, an OpenJDK project that is focused on improving startup and time to peak performance of Java applications. Fully covering Project Layton would itself be a subject fit for an entire episode of Stackwalker, though my colleague Nikolai also gives a brief summary of Project Layton in an Inside Java newscast video. CDS is an interesting and unfortunately often overlooked feature in the JDK. When I do bring up CDS during my presentations, rarely do I see more than a single person raise their hand saying they have heard of it. CDS does not offer the huge improvements to startup performance that is promised by some other options I covered at the start of this video, the low double digits like in the Spring Boot Pet Clinic example earlier being fairly typical. However, CDS is a simple and robust implementation, and its ability to be used in a variety of situations means it should be a feature more developers should look to take advantage of when looking to improve startup performance, as it doesn't come with those invisible dangers like forgetting to implement an undocumented requirement during a refactor and having those difficult conversations with your project lead or manager where you have to explain how this initially simple refactor has slowly devolved into a toxic smoldering pile that is going to consume many hours and resources to resolve. And with CDS being a cornerstone of a key future OpenJDK projects like Project Layton, getting operational familiarity with CDS now can help prepare you for the future of the JDK. Until next time, have a good one.